Hello, this is a question from Topology, and this question came in the last NTA NET December 2019 examination. This is a part C question, and question ID is 187980180. So let's see the question. Consider box n equal to 1 to n given with the discrete topology, and capital X equal to product of this box n where n running from 1 to infinity with the product space with the product topology for x equal to a1 a2 and x belongs to capital X. Define the map t from capital X to x by t of x equal to 1 comma a1 comma a2 and so on. Then which of the following options are true or is true? Option 1, let xn be a sequence in x, then it is convergent. And option 2, x is a compact Hausdorff space. Option 3, the map t from x to x is continuous and the map t has a unique fixed point. So before go to the solution, we recall few results from topology, and these are basic results. So the first result is, if each x alpha is a Hausdorff space, then the product space x alpha is also Hausdorff space both in the box and product topology. And the second result is a famous result, and this is called as a Tikhonov theorem. Any product of compact spaces is a compact in the product topology. And third is continuity, and this is also in the product topology. F is a function from a topological space to the product space given by the equation fa equal to f alpha of a. Alpha belongs to the index set J, where each f alpha is a mapping from the space A to x alpha for each alpha. Then f is continuous if and only if each f alpha, that is each coordinate function f1 f2, is continuous. So first we need to see what this set X looks like. The set X is box 1 into box 2 into box 3 into box 4 and so on. And box 1 contains the singleton 1, box 2 contains these 2 points 1 and 2, box 3 contains 1, 2, 3 and so on. And this is x1 and this is x2 and this is x3 and so on. And a basic open set in X is of the form, with respect to product topology, U equal to U1 cross U2 cross dot 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 cross UK, and after that K is a finite number. UK plus 1 is equal to the whole space xk plus 1 and so on, where U1 is open in x1 and U2 is open in x2, and in this way UK is open in xk. So U1 has one choice of subsets of open subsets in x1, and that is singleton 1, and U2 has two choices of open set subsets in x2, that is singleton 1 and singleton 2. In this way U3 has 6 choices, and namely singleton 1, singleton 2, singleton 3, and the set containing 2 points 1, 2, 2, 3 and 1, 3. In this way UK has 2k minus 1 minus 1 choices in the choices of open sets in xk, and after that xk plus 1 is the whole space k plus 1. Now first of all we prove that the set X is Hausdorff. For that, for each n is a finite natural number. The box n is a set containing natural numbers 1 to n, and it is given with the discrete topology. So a basic open set in box n is of the form or are singleton 1, singleton 2, singleton 3 and so on, finally singleton n. Now to prove that for each n the box n is the Hausdorff, we take any two arbitrary points from the box n, say x and y. Then obviously there always exist two basic open sets in the discrete topology, singleton x and singleton y, containing the points x and y such that their intersection is empty, which proves that the single box X, box N is a Hausdorff space. So box N is Hausdorff for each N. N is a finite natural number. So the result that we have seen in the beginning are mentioned here, that any product of Hausdorff spaces is a Hausdorff space in the product topology. So box 1 into box 2 and so on into box N and so on is a Hausdorff space in the product topology. So X is Hausdorff. Now we will prove that X is compact for each N. N is a finite natural number. Box N is a set containing these points 1 2 dot 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 N, and which is a compact set because N is finite and finite sets are always compact. And so the result or the statement from Tikhonov theorem, the product box 1 into box 2 into box dot 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 into box N into so on, the set X is a compact set in the product topology. So X is a compact Hausdorff space and option 2 is correct. There is another alternative way to prove that X is compact and the map T, which is a map from X to X, is continuous map, but we will not discuss the alternative here, as the video getting too longer. We leave only images of the alternative proofs. So they are now we will check the continuity of T, whether T is continuous or not. Whether T is continuous or not. We already seen that T is a map from capital X to X, and T of X is defined by 1, A1, A2, where X is of the form A1, A2 and so on. Now to prove that T is continuous, we define a map very similar to the projection map. So we define pi alpha, which is a map from X to X alpha by pi alpha of X, that is pi alpha of A1, A2 and so on, is 1 when alpha equal to 1 and equal to A alpha minus 1 when alpha greater than equal to 2. In particular, if we take alpha equal to 1, then pi 1 is a map from X to X1, and pi 1 of X, that is pi 1 of X, is a map from pi 1 of X equal to pi 1 of A1, A2 dot 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 equal to 1 from the definition. And similarly for alpha equal to 2, pi 2 is a map from X to X2, and pi 2 of X, pi 2 of A1, A2 is A1 from this definition as alpha greater than equal to 2. Now we see that in this way each pi alpha is continuous. So Tx equal to, moreover Tx equal to pi 1 of X, pi 2 of X and pi 3 of X and so on, and each pi alpha of X is continuous. So the result we have mentioned in the beginning, that is result 3, if T is continuous, then its coordinate function, that is pi 1x, pi 2x, pi 3x, each of them are continuous. Here each coordinate function is continuous, that is pi 1x, pi 2x and pi 3x continuous, hence T is continuous. So option 3 is correct, that is T is a continuous map. Now we always find a fixed point in X. The point is 1 1 1 in all its coordinate position, and we see that T of 1 1 1 is the point same 1 1 1, and this point 1 1 1 is a fixed point of X, and which is also unique according to the definition of T. You never find any other point of X which is also unique. So the option 4 is correct here. Now finally we are trying to prove the option 1, that is any sequence in capital X is a convergent sequence. We countered this option by a suitable example. We define a sequence xn equal to, where x1 equal to 1 1 1 1, x2 equal to 1 2 2 2, x3 equal to 1 1 3 3 3, x4 equal to 1 2 1. In this way, actually I am constructing it in this way. In the first position there is only one choice, and this is 1, so I put 1 1 1 1 1 1 1. And in the second coordinate position there are two choices, and they are 1 and 2, so I am putting 1 2 1 2 1 2. Similarly, in the third coordinate position, in each xn there are three choices, and so I am putting x 1 2 3 1 2 3, and continuing in this manner I am constructing this sequence xn. Now we will see that the sequence does not converge to any point in X. Suppose, to contrary, that xn converges to this particular point a1, a2, a3, a4 and so on, and name the point as X. So as X is Hausdorff space, then this point is unique. Now then there exists a open set U containing that point X such that xn belongs to U for all n greater than equal to j, where j is a natural number. That which means that after jth step all the xn's are belongs to this particular open set U, and any open set U in this product topology is of the form u1 cross u2 dot 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 uk cross xk plus 1 cross xk plus k plus 2, in this way, where u1 to u1 is open in x1, u2 is open in x2 and so on, and uk is open in xk. Now thus according to the definition, this open set U containing the point X, so a1 belongs to u1 and a2 belongs to u2 and a3 belongs to u3 and so on. For convenient, which in particular there are two choices of u2, that is u2 may be either singleton 1 or it may be singleton 2. We take u2 equal to singleton 2, and suppose xj belongs to u. So in the coordinate expansion of xj, the second coordinate is 2, that is xj is of the form 1 2 dot dot dot. Then after that, after the next immediate coordinate xj plus 1 is of the form 1 1 and so on, because as we define the sequence in this manner. So xj plus 1, this is does not belongs to u, because u1 belongs to 1, all right, but 1 does not belongs to u2, because we choose here u2 equal to singleton 2. So xj plus 1 does not belongs to u, hence the sequence xn does not belongs to the point, any point in X. So option 1 is wrong.